One final problem with just fundamental vector value functions is being able to create and parameterize a line segment. And this doesn't seem like it would be that difficult, and it's not, but it's going to be very important to us, especially later in the course when we start talking about vector fields, where we start to have multivariate sorts of vector functions. So let's take a look at just two line segments, and I'm going to show you how to parameterize those line segments. So we have a point P, we have a point Q, initial terminal, and we would like to be able to parameterize this line segment. And what we're going to do is we're going to go back to something we learned earlier when we took a look at the idea of being able to create these lines in space. All right, so let's just go ahead, and you might remember that we had these equations. One of the equations was that x equals x naught plus a t, y equals y naught plus bt, and z equals z naught plus ct. And these were the parametric equations of a line. All right? Now we don't want the entire line, we just want to parameterize the function. All right? So let's just use 0, 0, 0 as our x1, our x naught, y naught, z naught. Those are our initial points. And to figure out the direction numbers, a is going to be initial minus terminal. So 3 minus 0. B is going to be initial minus terminal. And C is going to be initial minus terminal. So that's going to be 3, 1, and 2 respectively. So if I were to throw these back into our parametric equations, we're going to get that x is equal to 0 plus 3t, or just 3t. 0 plus 1t, or just t, and then finally z is going to be equal to 0 plus 2t, or 2t. All right, now these are the equations of the lines, but that's not a vector value function yet. All right, to put it as a vector value function, r of t, all we're going to do is just take each of these, 3t, t, and 2t, and those are going to be our coefficients of I, j, and k. So we get 3ti plus tj plus 2tk. Now this represents the entire line, the vector, but it's the entire line. But we don't want the entire line. We just want the line segment from 0, 0, 0 to 3, 1, 2. The technique that I've shown you will always produce a segment if t ranges from 0 to 1. So you have to specify the domain. Right? Of course, if you want to check this, what you can do is you can just go to the vector function plotter that I showed you from GeoGebra, and then just scroll from 0 to 1 to kind of get an idea that this does start at 0, 0, 0, and it does end up at 3, 1, 2. All right. What if the points are not the origin and another point? Okay, so we have this. So let's just define x naught to be negative 2, y naught to be 5, z naught to be negative 3. A is going to be terminal minus initial, negative 1 minus a minus 2, and that's going to be 1. B is going to be 4 minus 5, which is negative 1, and C is going to be equal to 9 minus a minus 3, which is 12. Right? So we can parameterize the vector, the line, by saying x is equal to negative 2 plus 1t, y is going to be equal to 5 minus 1t, and z is going to be equal to negative 3 plus 12t. That's the entire line, but we don't want the entire line, and we also want a vector. All right, so to parameterize this, we're going to say r of t is going to be equal to negative 2 plus t I plus 5 minus t j plus negative 3 plus 12t, and I'm going to have to try to rewrite that a little bit closer to the plus sign so I can squeeze that k in there. So that's going to be negative 3 plus 12tk. Right? And of course, this is only valid under a specific parameterization. And the parameterization that we're looking at is when t ranges from 0 to 1. So again, when you're building these line segments and parameterizing them as a vector value function, make sure you give both the equation of the function, but also a domain. And it's always going to be 0 to 1 with using the technique I showed you. All right. We're going to start talking about finally some calculus of these vector value functions. And we're going to talk about the idea of continuity, and we're going to talk about the idea of limits. You might remember from Calculus 1, continuity means that the limit exists, or in other words, it's in the domain of the function. All right, so, and very similar to the problem we did earlier, where we just found the domain of each of the different components, we could do the exact same thing here. All right, so let's start with continuity and then we'll finish up with limits. So we have a vector function, and what I'm going to do is I'm going to start by finding the domain of root t, and I'm going to find the domain of root t minus 1, and I'm just going to sandwich those. All right. Now we know that we can only put real positive numbers or 0 under a radical, so for the first, or at least an even power radical. So for the first one, t has to be greater than or equal to 0. For the second one, t is greater than or equal to 1. Right? Now, if we sandwich these together, the only one that really matters is t is greater than or equal to 1, because there are some numbers, for instance, 0.5, that if you were to plug that back in for t, that would not fit into the domain. In other words, it wouldn't be valuable. Right? So the domain for this function is going to be bracket 1 to infinity. Right? We use the bracket again just because we're including the 1. Right? Down here, we have 3 functions. We have e to the minus t, we have t squared, and then unfortunately we have this tangent of t. And that's going to be the one that we're not going to like too much. All right. Domain of e to anything, as long as it's a polynomial, is going to be all real numbers. Okay. T squared is a polynomial. Domain of all polynomials is all real. And we know that the tangent function does not exist at pi halves, 3 pi halves, 5 pi halves, okay? Anything with a 2 in the denominator and an integer pi. All right, forever. And so if I wanted to write the domain of this, okay, what I would do is I would start a pattern. And I don't know if any of you have ever seen this before, but what you do is you have a pattern. So we're going to say dot, dot, dot. We're going to say union pi halves, 3 pi halves, union 3 pi halves, 5 pi halves, union dot, dot, dot. And so what that does is it establishes a pattern. And usually in mathematics, to establish a pattern, you have to have at least 2 of the elements in the set to start the pattern. All right. So hopefully this gives you a good overview as to how to parameterize a line, and then also with respect to continuity. In the last video we're going to take a look at how do we evaluate limits of vector value functions.